Hi there and welcome to our webinar today, Maternal Nutrition. I'm Jane Byrne, Senior Editor, FeedNavigator. The format of today's webinar will be two presentations, each of 15 minutes duration. They will be followed by a 10-minute panel discussion, and then it's over to you, the audience, for our live Q&A session, where you get to put your questions directly to our speakers. You can start sending in those questions as soon as the presentations begin. Now, we are starting to hear a lot about transgenerational or maternal nutrition in all species and how such an approach can benefit the performance of the progeny. But there's still a lot to learn and explore about this field of research, which makes it an interesting topic for us to cover today. As we all know, the large litter sizes of today's hyper-prolific sows can often result in the birth of small and or underdeveloped piglets, which have a higher mortality and slower growth rate. So industry is exploring how it can enhance the diet of the sow during gestation to improve the nutrition of those small piglets in the uterus and thereby reduce the percentage of small piglets at birth and improve their performance thereafter. Recent findings have indicated that feeding sows organic trace minerals during gestation can improve the fetal and postnatal development of piglets. Dr. Xu-Xing Shen, Senior Manager Novus, will present on behalf of that company on those research findings today. In another presentation, Dr. Pedro Uriola from the University of Minnesota in the US will look at the benefits to the progeny of feeding the sow with fiber. He will also discuss the impact of feeding gestational zinc to sows and how that can improve the pre-weaning survival of low birth weight piglets. Okay, so let's kick off. It's over to you, Dr. Shen.
Hi everyone, this is Juxin Chen from Novus International. I will first introduce myself a little bit more about my background. I have background training in cell and molecular biology. My projects at Novus mainly focus on maternal feeding, epigenetics, gut health, meat quality, and lameness in poultry, swine, and ruminants. Today I'm going to talk about maternal feeding and the chelated trace minerals on cell progeny development and growth. This is the overview of my talk today. So first, what's maternal feeding? I'll give some definition here. First, fetal programming is a concept that maternal nutrition or stress can alter the fetal development, and this can create long-term or permanent effects on the offspring. For example, something like a protein limitation can actually decrease muscle development and also reduce birth weight. And the maternal zinc deficiency, they can impair fetal development. They also reduce appetite and also compromise immunity. Therefore, they could increase the risk of disease. And environmental heat stress during gestation can actually cause pregnancy failure. They can also reduce the growth rate and fetal development as well. So that means that some maternal feeding, they may be able to positively regulate those fetal program challenges. Therefore, they can improve fetal and postnatal development and growth later on. Another technology I'm going to introduce is epigenetics. First of all, we all know that genetics is determined by DNA, and the genes are the specific DNA sequence which will be activated when they're expressed. That means that gene expression means the genes are in active state so that they can make their own product, protein, at the end. So epigenetics means that you can turn on or turn off gene expression by different mechanism without altering the DNA sequence. Let me give like an analogy about epigenetics. So the DNA is like your recipe book for your body, and the genes are like ingredients in the recipe book, and the epigenetics means it's like a cook, so like a cooking. So all of the ingredients needs to be balanced, and also they need to be added at the critical time. So different cook can cook the food with different tastes. It all depends on how much ingredients were added and when to add the ingredients. I hope that will help you understand what's epigenetics. So there are different ways to regulate epigenetics. So like DNA methylation or histone modification, there are two common ways of epigenetic modification. I will elaborate more in detail later. There has been reported that nutrition could regulate epigenetics, thereby they can upregulate or downregulate gene expression. And the epigenetics actually can happen everywhere or even in our daily life. So it can occur in the breeder or progeny alone, and they can also occur from the breeder to the progeny. And we know that developing fetal or embryo, they are prime target of epigenetics. If we can optimize maternal nutrition, and then we can optimize fetal programming by regulating epigenetics. And I'll give example in next slide. So in nature, where a worker bee, if a worker bee can become queen if we feed the worker larva with royal jelly, and that will make like worker larva becomes queen at the end. And the mechanism behind is epigenetics. Here's your diagram shows the DNA wrap around histone form a chromosome. For the worker bee, so their queen gene is highly methylated. So that makes the DNA and histone form very compact structure. So the queen gene is inactive. So that's why they are worker bees and not a queen. If we feed royal jelly to the worker larva, so they basically reduce methylation. Basically, the methylation of DNA is becoming less. So which makes the DNA and histone form like a more relaxed structure. So the queen gene, they have access to the RNA polymerase and also some transcription factor that makes the queen gene's expression activated. Therefore, the worker larva becomes queen. So that's basically give example how nutrition can modify epigenetic tags on the DNA or on the histone. Therefore, they can upregulate or downregulate gene expression. It's like you're flipping a switch. So that's where actually the power of nutrition. So next, I'm going to move on to challenges of hyperprolific cell. So we know that with really advanced in genetic selection for high productive cells, the number of piglets per cell per year is increasing dramatically over the last 10 years, especially in Europe, as you can see from this graph. So the number of piglets per cell per year increased by 4 piglets. That indicates that the cells are becoming more and more prolific. So with increased litter size, actually create some challenges to the swine industry. For example, with increased each one piglet in each litter, the body weight of piglets were reduced by about 100 grams. And also the CV of birth weight also gradually increased with increased litter size. So that means that increased litter size not only reduce birth weight, also reduce uniformity. As we mentioned in last slide, genetic selection for high prolific cells that will increase litter size. They will reduce uterine placenta blood flow. That would increase the number of ram piglets by about 15 to 20%. Those piglets have less than 1.1 kilo body weight. So study has shown that those ram piglets, they have high pre-weaning maternity. And Dr. Wang's studies showed that the relative weight of skeletal muscle and small intestine to their body weight was significantly reduced in no birth weight piglets compared to normal birth weight piglets. And another study shows that the 0.4 kilo difference in birth weight, they can be translated to 1 kilo difference at 35 days after birth. That means that low birth weight not only impair tissue development, they may have high mortality, they also have compromised postnatal growth. If we can optimize nutrition in the maternal feeding, maybe we can overcome some of those issues. So this diagram shows lifespan of the pig. As we can see from this diagram here, from like 14 to 18 days after ovulation and fertilization, embryos start to attach the uterus. Of that attachment, the fetal development and growth is mainly dependent on maternal nutrition. And during lactation, mammary development and milk production is also dependent on maternal nutrition as well. And in meat animals, one of the very critical commercial objectives is muscle development. And we know that the number of muscle fibers increase during gestation stage, and the number of muscle fibers is fixed at birth. So increase or sufficient maternal nutrition can maximize the number of muscle fibers that will help increase muscle mass at the end. And after birth, the muscle growth is mainly dependent on muscle fiber hypertrophy by increased muscle fiber diameter and length, which would lead to higher muscle mass at the end as well. And another important organ is the intestine. So from gestation to 3 months after birth or critical window of gut development. And we know that if we can optimize or give sufficient maternal nutrition, we can make the pigs have a better start with their gut development and better immunity. That would actually help to reduce weaning stress or reduce inflammation or reduce pathogen infection later on. That will reduce the risk of the disease. And the trace minerals, they are cofactors of a lot of enzymes. They could play pretty important role for the fetal development and postnatal growth, especially for the muscle development and gut health. So next, I'm going to show some of our data about the impact of maternal chelated trace minerals supplementation on protein development and growth. In this particular trial, we have 2 sister cell forms, and one form was supplemented with ITM, and another form will replace 50% ITM with chelated trace minerals. The mineral lists were shown on the right side here. So first we look at the piglet birth weight, and then we want to know postnatal growth with the cell nutrition different program here. So in this particular part of study, so we bred 300 cells to provide 1,200 weaned piglets with similar body weight across 2 different farms. Those 2,400 pigs were fed with the same diet with ITM from wean to market. As you can see here, supplemented chelated trace mineral to the cell increased birth weight by 9%. It also reduced the percent of birth weight less than 1.1 kilo by 29%, which indicates that feeding chelated trace minerals to the cell improve piglets' birth weight and also uniformity. So let's look at the postnatal growth. As we mentioned earlier, the pigs started with similar body weight at weaning. And as you can see from this graph here, at all time points, when the cell fed with chelated trace minerals, the pig's body weight always increased. And the heart rate there increased by 2 kilo. And they also have 1.8 kilo more carcass weight when chelated trace mineral were fed, and they also have a great loin eye area. That's a very important parameter of the muscle quality in pigs. So that indicates that progeny-fed cells with chelated trace minerals have higher growth rate and hot carcass weight. They also have better loin eye area as well. So next, we would like to know the mechanism behind how chelated trace minerals regulate gut health and muscle development in progeny. In this part of the study, we have 2 groups of cells. They're fed either inorganic trace minerals or chelated trace minerals from 35-day post-conception until weaning. The chelated trace mineral treatments actually have 50% chelated trace minerals and 50% ITM. So we sacrificed 16 piglets at birth and 16 piglets at weaning, and we collected genome to measure some inflammation-associated gene expression. We also collect some muscle to measure global histone acetylation and muscle growth-associated gene expression. So we know that one of the key pathways that regulate inflammation is called NF-kappa B pathway. NF-kappa B is a molecule that actually mediates inflammation. So this is the simplistic view of NF-kappa B pathway. So basically, NF-kappa B can be stimulated by the extracellular stimuli. So for example, virus infection or bacterial infection or some inflammatory cytokine, they can all increase NF-kappa B gene expression inside the plasma. So NF-kappa B can then translocate to nucleus, and where they can stimulate pro-inflammatory cytokine expression. So then they will stimulate inflammation in the animal. So basically, take-home message is if you have higher NF-kappa B, so the animal may have higher inflammation. So in our studies, what we have found that feeding chelated trace mineral to the cell, we see less NF-kappa B gene expression in weaning pigs. So that means the pigs have less intestinal inflammation. That concludes that if we supplement the chelated trace mineral to the cell, they can reduce jejunum inflammation in weaning pigs. We also found that if we fed chelated trace mineral to the cell, the global histone acetylation will increase in the muscle of the pigs at birth, and the greater histone acetylation actually make the histone and the DNA form more relaxed structure. So the genes on the in the muscle, they get access to more DNA RNA polymerase or some transcription factors, so making them be active, and then those genes can be expressed. So unlike the other example I gave in the queen and the bee, so those epigenetic modification happens on the DNA. In this case, epigenetic modification actually happens on the histone. So basically, the increased acetylation makes the genes be more actively expressed. That means they have like a more active muscle development when the cell were filled with chelated trace minerals. That actually help us understand in our earlier slides, when you feed cell with chelated trace minerals, we see great loin eye area because we can make the muscle develop more active. To summarize the mode of action here, for maternal feeding on progeny development and growth, if we feed trace minerals to the cell, in the intestine, we see reduction of NF-kappa B gene expression, which indicates less intestinal inflammation. In the muscle, we see greater hypertrophy, which for the sake of time, we did not share data today. And we also see greater histone acetylation, which indicate muscle development and growth were improved. So with the reduction of inflammation, which means better gut health and better muscle development and growth, that contributes to better growth performance and carcass stress in progeny or in our other trials. So here are our opportunities. We know that the cells has been going through very advanced genetic selection, and to improve their productivity, and maternal nutrition could play a role. They can help them to reach their genetic potential. And the maternal chelated trace mineral supplementation, they can improve reproductive performance, embryonic development, which we did not share data today because of time constraint here. We do see that they can improve immunological capacity and also muscular development. So just like in nature, the phenotype of queen or worker bee, they can be determined by the nutrition of larvae. In our swine industry, if we include chelated trace minerals as part of a nutrition program for the maternal feeding, they can actually help to maximize productivity of cell and progeny through some of the mechanisms we showed today. Thank you for your attention. I'm happy to take questions that you may have.
My name is Pedro Urriola. Today, we'll be talking about sow nutrition and its impact on her progeny or on the sow's progeny. I work for the University of Minnesota, and I'd like to talk a little bit about myself before we get into the topic. I come from Venezuela with a veterinary degree. I study master's and PhD here in the United States, and my professional goal is to help feeding 9 billion people, of many of them who can afford to eat meat, and we would like to do this without depleting natural resources. We have created a integrated animal systems biology team. Our team is using molecular analytic techniques to understand how animals respond to diets and their environments. Today we are going to talk about how does the mother ensure success of the offspring, or how maternal nutrition affects piglet performance. And I have divided this into effects preconception, in utero, colostrum quality and milk quality, and behavior. So these are 4 ways as to why or how a mother can ensure the successful of the offspring, or the dam can ensure the success of the piglets. Getting right into topic, feeding sugar beet pulp has been observed to increase the number of piglets live born. In these experiments, they were using unmolasses sugar beet pulp, feeding 20% during lactation, and then 40% of the diet was made of sugar beet pulp in the wean to estrus periods. And these researchers observed that they get almost one one piglet more, or increase in the number of live born piglets. As a matter of fact, in collaboration with Novus International, we wrote a chapter for a book that they have published recently, and we reviewed the literature to see how much impact has been on the effect of dietary fiber in the diets of sows on the number of pigs total born and born alive. And we did observe that across multiple experiments, on average, there was a 0.29 increase in the number of total born pigs and 0.28 in born alive. Unfortunately, as we did this work, we look at the level of NDF intake, or a measurement of the fiber intake, neutral detergent fiber intake, and we couldn't see a level of NDF intake upon which we saw a difference in the number of pigs born or born alive, meaning that there is an effect, but today we cannot tell at what level that effect exists. And partly could be because the effect seems to be diet dependent. In this experiment, these researchers fed wheat bran and lupins, and they observed that the maturation of oocytes, the process upon an important process for obtaining an increase in litter size, the proportion of those oocytes that reach maturity was greater in sows that consume lupin fiber, or fiber based on lupins, than when they consume fiber based on bran. And therefore, it's likely that the effect of fiber on embryonic development and subsequent number of pigs born or born alive could be diet dependent. And this group also observed an increase in the pigs that were fed, or numbers of pigs born alive from sows that were fed lupins. Other researchers have observed that if they increase the amount of fiber that they feed to sows prenatal or before farrowing, they don't observe an increase in the number of pigs born or total born alive. However, they observe a decrease in pre-wean mortality. And that decrease in pre-wean mortality appears to become the result of a decrease in the number of stillborn piglets and subsequent survival of the piglets from sows that were consuming fiber towards the end of the gestation, in which the piglets of low vitality there was less proportion of piglets of low vitality, and therefore overall greater survival of piglets and overall less pre-wean mortality when sows consume fiber pre-farrowing. And there are other causes of why those piglets have less survival post-weaning or during the lactation period. These two piglets are litter mates, and even though as embryos they may have developed with similar environment, as they were growing in utero, this little guy suffered what is being mentioned in the literature as intrauterine growth retardation. And we do know that those piglets that suffer decrease in their growth intrauterine and that are born with less than 1 kilogram of body weight, so if at birth they have less than 1 kilogram of body weight, the probability of them dying pre-weaning is quite high. So as piglets get lighter, the likelihood of dying is greater, and 1 kilogram seems to be a breakpoint. However, if we see on overall productivity of those animals, in this case as measured as the days to reach 93 kilograms, we see that the probability of animals reaching this high productive level increase with birth weight. So maternal nutrition can help probably to improve the productivity of the animals, not only by changing their body weight, but the subsequent productivity. One of those nutrients, micronutrients important in sow diets is zinc. And therefore, we did a zinc balance study where we study sources of losses of zinc during late gestation and lactation. We observed that at day 80 of gestation, when sows were consuming a diet that was not supplemented with zinc, the zinc that these sows were consuming came from the ingredients in the diet like corn and soybean meal. We observed that these sows had actually a negative value for digestibility of zinc, and they were excreting more zinc than they were retaining. So they were in a negative zinc balance towards late gestation. Lactating sows, on the other hand, had a higher feed consumption, higher consumption of zinc, higher fecal excretion of zinc, but actually a positive digestibility of zinc, excretion of milk, zinc or production of milk, and therefore some zinc is lost into milk. But interestingly, these sows, even though they were producing milk and putting zinc into milk, they actually had a positive zinc balance compared to sows in late gestation. So we did another experiment. These sows, on the other hand, were fed three types of diets. A diet with 125 ppm of zinc. This is about the level or the requirement established by the National Research Council, or NRC. 365 and 595 ppm of zinc additionally in the diet of those sows. And we observe that the piglets from these sows that were consuming high levels of zinc on day 75 and on of gestation, thus the piglets from these sows had lower pre-wean mortality. That changes from 15% all the way down to 12%. And interestingly, the decrease in pre-wean mortality was greater of magnitude among those piglets of less than 1 kilogram of body weight. Another way that we can improve pre-wean mortality or post-wean development of piglets is by coordinating the sow diet and the piglet diets with elements that help piglets develop their capacity for growth post-weaning. In this case, we fed sows with capsaicin. Capsaicin is an extract of capsicum, and we have sows fed the traditional control diet at our university farm and a diet supplemented with capsaicin. And we divided piglets from these sows into two groups: piglets that consume the control diet, so they continue in the traditional university program; piglets that were which nursery diet was supplemented with capsaicin; and then piglets that were coming from capsaicin fed sows that were split into control or fed capsaicin. Interestingly, we observed that those piglets whose mothers had been consuming capsaicin, so sow fed capsaicin and nursery pig fed capsaicin, had an improvement in gain to feed post weaning, meaning that if their mothers were consuming capsaicin, they had a better response to the supplementation of capsaicin in their diets, suggesting another way of how sows or sow maternal nutrition can influence piglets post weaning. So, in summary, we've talked about dietary fiber can increase pigs born alive, decrease pre-wean mortality. However, it seems that this effect is source of fiber dependent. Feeding high fiber level feeding high levels of zinc pre-farrowing decrease pre-weaning mortality, especially in low birth weight piglets. And coordinating the sow lactation diet with the nursery pig diet may be another strategy to decrease pre-wean mortality. I want to finally invite you for our conferences this fall, the Island D. Lehman Swine Conference or the Minnesota Nutrition Conference. Thank you.
Thank you to our speakers, Pedro and Xuxing, for those very interesting presentations. I think you would agree there's a lot of content in there to mull over. And remember, the webinar is available to download from here and over the next couple of months, so you can review those presentations at your leisure. To my mind, there's still a lot of uncertainty as to what are the most effective sources and properties of dietary fiber for sow diets to induce changes to the endocrine system, to improve embryo survival and increase litter size. Well, what are your thoughts on that, Pedro?
Oh, that's a good question, Jane. Yes, as we think of how the diet can affect subsequent generations, one in this theme of transgenerational effects of diet, one of those aspects that people have talked about or where we came with this idea is on energy and dry matter intake. And to kind of recap where we came to know about epigenetics or how the diet of the mother affects the offspring was back in the early days of the war, where there was a large group of people with hunger in Europe. And subsequent generations, they have seen metabolic issues in those people. And so what that tells is that perhaps energy or caloric intake has an effect on uh, on on the development of the offspring. So fiber is a way to control energy intake. So to some extent, people have thought, well, fiber can affect the offspring because the mother will have a different energy intake, but not to some extent, because there are different sources of fiber in which you could have same level of energy intake but different outcome on the output or the effect of that fiber on embryo development. So it seems that not all fibers can do the same. The fiber that people have tested the most has been sugar beet pulp, and rightfully because it's the most available in Europe, let's say so. For us in North America, it's a little more tricky because sugar beet pulp is not as available. Therefore, if somebody in North America or in other countries would like to test ways to improve litter size, for example, um, then we will have to find other sources of fiber. And it seems that insoluble sources of fiber make the most beneficial effect, um, but partially so we still need to test which one of those are the ones that makes the effect, the best effect.
Okay, and are there procedures or processes under development to help nutritionists in feed companies better determine the physical and chemical characteristics of dietary fiber in feeding ingredients in order to get this effect that we've been talking about, to try and maximize the feeding strategy for sows based on fiber with a view to improving the performance of the offspring?
Yes, yes. So, for example, there are properties of fiber like physical chemical properties like viscosity, right? We all have seen how oats, when we mix with milk in the morning, for example, makes a gruel that is viscous. So that viscosity is a property of fiber that is connected to some of the impact of fiber on the gastrointestinal tract. We at the University of Minnesota are trying to understand how these physical chemical properties like viscosity, for example, could be tied to elements of gut health. Or in the case of late gestation sow or late gestating sows, to, for example, insulin resistance, because insulin resistance is a natural occurrence in late gestating animals where the mother goes through a period of this insulin resistance. However, that has an impact on subsequent lactation feed intake, and therefore helping the mother cope with that insulin resistance through the utilization of fiber could be of benefit. The type of fibers that have an impact on this insulin resistance appear to be those that have high viscosity value. A lot of the roots um, uh, or mannans that have high property or capacity for viscosity, for inducing viscosity, seem to be of benefit.
Okay, I just want to let the audience know that they can start sending in their questions straight away to our two speakers, to both Pedro and to Xuxing, through the question and answers tab on the right-hand side of the platform. And also Novus has a handout for people to download, again in the handouts tab on the right-hand side of the platform. So I just want to ensure that we've covered this topic of fiber quite comprehensively before we move on to look at organic trace minerals. Pedro, in a recent review of using fiber to enhance the productivity of sows, you referenced the use of konjac flour and a study that showed the inclusion of konjac flour increased during the gestation diet. There was a linear increase in the number of piglets weaned, in the pre-weaning survival rate, and in the litter weights on day 14 of lactation. So that use of konjac flour actually achieved quite a substantial outcome. What's the mode of action there?
Yes, we wrote that for a book that we work in conjunction with Novus International, and it's called, I think, Feeding Hyperprolific Sows. And yes, in that we reference this study upon which the feeding konjac flour, which if we look at the type of fibers, konjac flour is one that induces a lot of viscosity. Those oligosaccharides, when they enter into a liquid mix, for example, in the gastrointestinal tract, they turn very viscous. And it seems that that viscosity is linked to decreasing the impact of insulin resistance on the mother, and so probably better feed intake of the mother during lactation. And that better feed intake of the mother during lactation leads to better milk production and better milk productivity. there are some thoughts that also other aspects of fiber can enhance the immune system of the mother by stimulating better immunoglobulins or modulating the immune system, and therefore improving the survival of the offspring. So there, but a lot of times just simple better feed intake is a big impact.
And the use of dietary fibre in late gestation, that also might improve the colostrum quality in sows. Is that the case then?
Yes, yes. There has been studies where they look at feeding fiber in late gestation and improving colostrum quality. And because colostrum is being produced hours or before farrowing really starts. So any intervention that hits that window of time may help to improve the colostrum quality, and also number of stillborn pigs, because as these hyperprolific sows, they have larger litters. So there is a long window of time between the firstborn and the last piglet born. And it seems that dietary fiber helped the sow keep more energy in herb, because DFAs and dietary fiber delays the onset of energy, and therefore it may help to normalize the level of energy in the sow and allow the sows to have better ability to farrow during longer farrowing period.
Okay.
And
yeah, continue. Sorry, I didn't mean to stop you there,
no,
Pedro.
no, and that's a work on from Denmark, from Peter Thiel in Denmark, and they test and see that yes, it seems that it helps to decrease number of stillborn.
Okay. Well, don't go away, Pedro. We'll be coming back to you, but I just wanted to get Zhu Xing in here. Nice to see you, Zhu Xing. So obviously, you're representing Novus, and your focus will be chelated trace minerals, chelated organic trace minerals. Can you talk to us a little bit about that? About what are the benefits of using chelated trace minerals in the sow's diet for the offspring?
Yeah, so we have been focused on the chelated minerals supplementation in sows on multiple studies. So basically, what we have seen that if you supplement trace mineral to the sows, which including the zinc, copper, and manganese, from the gestation stage until lactation, what we see that in the progeny, the piglet's birth weight increase, and also the uniformity also increase. Because we have done that if we feed the two forms with one inorganic and one organic minerals, and we look at the birth weight, they are increasing, and the uniformity is also increased. If we look at the postnatal growth, if they feed, say, with the ITM or inorganic from the sow, but the progeny feed the same diet with ITM, so their postnatal growth is better. They grow faster, and they have higher growth, higher carcass weight, and also higher body weight at harvest time. And we also look at what the beneficial effect in the progeny in terms of the mode of action. Then we look at gut health and muscle development, because gut health is very important, because it's really in the earlier stage. Better gut health, they can better manage the pathogen infection later on, and also manage better gut microbiota as well. And in terms of muscle, and we know that the number of muscle fiber is increased during gestation, but number of muscle fibers is fixed at birth. In order to have higher muscle yield at the end, so we need to increase maximum number of fibers at gestation, and then promote their growth later on postnatally. So basically, what we see, you supplement the trace minerals chelated form in the sows, we see they have less gut inflammation, so that means they may have less mortality. And then we'll also see that they have better muscle development at birth by increasing the histone acetylation, make the genes expression associated with muscle more active. That basically we see better muscle development. And then if we look at the muscle yield at the harvest, they have a great loin eye area. So that indicates the muscle growth postnatally is also better.
Okay.
So that's the main findings. Yeah.
But what is the mode of action? What is like the mechanism behind the effectiveness of organic trace minerals in the sow's diet?
Yeah, so we think that mode of action, one part is they have better gut health, because when we look at gut health parameter, look at inflammation, we found that if you feed the sows with chelated trace minerals compared to inorganic, so we see less inflammation. One of the indicator is less NF-κB gene expression, and NF-κB is a molecule that mediates inflammation. And then if the animal has external challenge like a passing infection, like a virus infection, bacterial infection, they can stimulate the NF-κB gene expression, and NF-κB can translocate to the nucleus, and then they can promote inflammatory cytokine gene expression, therefore induce inflammation. But if you use some of those chelated trace minerals, they can reduce NF-κB gene expression, therefore the intestinal inflammation is less, and that means the piglets have better gut health, and then they can better manage later challenge like weaning stress and so on. So that's one part, basically reduce inflammation and improve immunity. On the other part, because we know that one of the critical commercial objective for this pigs is the muscle mass. So we want the pigs to grow a lot of muscle. And what we found that if some of the chelated trace minerals in the cells, the prosody has better muscle development, because their muscle, like a histone acetylation, is increased. Some of gene expression associated with muscle development is also regulated, make them produce more muscle yield at the end. So that's the mechanism behind, we think. One is gut health, better gut health, another one is better muscle development.
We're going to go straight to our Q&A. We've got about 10 minutes left, so here we go. Greg has asked a question, Pedro, and this is directed to you. How much capsaicin was supplemented, and was it coated in fat or another encapsulation method?
Yeah, it was put at 0.5% of the diet, and it was not encapsulated this time.
Okay, and a question for you, Xuxing. This is not related, evidently, but are any of the epigenetic modifications heritable, or is it a single generational phenomena?
You're muted, Xuxing. Xuxing, you're muted.
Okay, sorry. So
okay, you might want to.
Some epigenetic effect can be inherited or long-term. For example, if the cells under heat stress during pregnancy, so then their offspring actually have a compromised protein deposition. They also grow more fat, and also they grow much slower to like 80 kilogram body weight at the end. So that means the effect on the cells can be really transferred to the progeny.
Okay, I'm just going to stay with you for another question, Xuxing. In terms of the chelated trace minerals on the impact on gut health, Pietro wants to know, can you elaborate on the mode of action of those trace minerals on gut health? Is it all about decreased intestinal inflammation?
So we found that the main mechanism of improving gut health is through reduction of gut inflammation, mainly through the NF-κB pathway. That happens not only in sow and the piglets, it also happens in breeders to the broilers, and also actually from the sheep, from the ewe to the baby sheep as well. It's a quite consistent cross species.
Okay, and I'm going back to you now, Pedro. Jasper wants to know, is using high levels of dietary fiber in lactation feeds, is that a process that would require specific enzymes?
Yes, many people have tested the use of enzymes to improve the energy of the fiber from fiber for lactating sows. So let's remember that the goal in lactating sows is to improve feed intake or maximize feed intake and energy in the diet that the sow will take, because that is related to milk production and the productivity of the sow. So yes, people have used enzymes to break down the fiber and improve the energy value of the diet. Obviously, different type of enzymes need to be applied to different types of fiber, and that needs to be coordinated or used in coordination, the type of fiber with the type of enzyme.
We're getting quite a lot of interest on the capsaicin side of things, Pedro. So I have another question for you. Was it pure capsaicin, or was it a bioactive? Was it in a diluted format?
Yes, the one that we were using was an extract of capsicum, and in many cases that will have different compounds, and so it was a mixture that we were using.
Okay, and now Xuxing, another question coming in for you as well. In terms of Ronaldo, he wants to know what is a more significant impact? Is it the trace mineral element of the sow's diet, or is it the energy source used in the maternal diet?
So I think the energy is definitely important, and we think that trace minerals is also important because it can have long-term effect. We know that we know the zinc, for example, can improve immunity. Copper can improve the collagen cross-linking, and also has antimicrobial effect. Like manganese, it actually can also improve bone development. And all three minerals, they can improve structure integrity, reduce oxidative stress, and also improve all kinds of structure and long-term effect. For example, we have I shown today, and also from other studies, we show that if you use something like a chelated form trace minerals, you can improve longevity of the girls. For example, they have higher firing rate, they have higher retention rate. And in terms of progeny, you can actually improve the birth weight and uniformity, and also postnatal growth. So we think that with trace minerals that not only improve the sow performance and productivity, and also on progeny and energy, I think for sure they are important too, because during like a last trimester of the pregnancy, have higher enough energy and the nutrient. They are important for fetal development and also for mammary growth as well.
Okay, I think this is going to have to be the last question. It's from Sherry Ann, and Pedro, it's for you. So you get to finish. What kind of zinc do you recommend to give similar benefits as based on the trial that you presented?
Well, in our trial, Jane, we use zinc sulfate, an inorganic trace mineral, because we wanted to have. But let's remember that in the U.S. there are no limitations to the level of zinc that we can add into the diet. In other latitudes or in other cases, if you have a limitation, probably using something that is more bioavailable, it will be better indicated, or will be a better option than a inorganic trace mineral.
Okay. Well, I think we're going to have to leave it there. Thank you all for your interest and for the flood of questions that we have coming in. And I'm sure when we run another webinar on this topic, we can address some of those questions. We can also address them via email after this webinar. So in summary, I think we see a huge potential for transgenerational nutrition. It really is a nascent field of research, but one that merits plenty of exploration, which I'm sure Pedro and Xuxing will address over the coming months and years. So thanks to our speakers, thanks to Novus for sponsoring, and thanks to you, the audience, for tuning in and for bearing with us for our technical difficulties at the beginning. Thanks to you all. Bye-bye. Tune in again.
Thank you.
Thank you. Bye-bye.